Hello everyone. Today I'm going to talk about multi-qubit quantum communication system for image transmission over error-prone channels. So my name is Professor Anil Fernando, representing the Computer and Information Science Department in University of Strathclyde in Glasgow, UK. So before I move to the presentation, I just want to give you a short summary of what I am doing in my research team. So I'm leading the research team of multimedia communication research, which involves lot of aspects of image and video processing and communication and quantum communication. Basically, my interest is like how the video communication can be done in different channel conditions in classical communication as well as in quantum communications. And also, this has been extended recently for the semantic communication applications as well. So before we start the presentation, so this is the kind of the content of the presentation: introduction, literature gap, research gap, aim and objectives, proposed framework, research, and some future work. So those who don't know about quantum communication, I just want to give you a very brief introduction on semantic so quantum communication and its application in media transmission. So there are two types of quantum communications: entanglement-based quantum communication and superposition-based quantum communication. And people have been working on entanglement-based quantum communication for some time now, but there's only a very little work has been done on superposition-based quantum communication, which is the topic that I'm going to cover today in this presentation. So, how does it work? So basically, quantum superposition work like prepare and measure-based communication system, mainly for targeting high noise resilience applications, high reliability, efficient use of bandwidth, low latency, fast and resource efficient media transmission. So what is the research gap? So the research gap is obvious because now every day we are consuming more and more channel bandwidth in classical communication systems. So currently we are reaching towards the saturation limit of classical communication bandwidth in different applications. So inadequate noise resilience of classical systems, particularly in high signal noise ratio environments, limited empirical studies on the application of quantum communication technologies for high quality media transmission, and underdeveloped quantum error correction techniques tailored to preserve the fidelity of media contents. And if I continue this, bandwidth limitations in classical communication systems, like I explained before, is the major hurdle for the classical communication systems. And that's why people have been looking some alternative. Quantum communication is one of the strongest candidate to resolve these problems. Lack of systematic analysis of the potential of quantum communication to improve both the efficiency and the quality of media transmission. And finally, the lack of research on the scalability of quantum communication systems for large-scale media transmission. Here in this presentation, we are only targeting the image communication, which has some kind of inherent features like spatial correlation and how the pixels are correlated to each other. We need to preserve this spatial correlation during the transmission to have a sufficient quality at the receiving end. So what are the objectives of this presentation? Basically, we are targeting to develop an end-to-end quantum communication system model that leverages quantum superposition to enhance noise resilience, improve quality and robustness of the image transmission under noise by replacing single qubit encoding with multi-qubit encoding. In the first part of the presentation, I'm focusing about the single qubit encoding, and then latter part of the presentation, I'm considering the multi-qubit encoding. And finally, provide a comprehensive analysis of the advantages of quantum communication of classical systems, focusing on the ability to transmit image, large volume of high quality media data, in this case, image. So what is the background? So it's very difficult to explain how the quantum works in a presentation like this, but This figure represents the basic differences between the classical and the quantum communication systems. The classical world is quite simple. It's a linear representation of the information. Uh, People have done a lot of work on classical systems to witness the present day communication systems. But quantum world is quite different. It's non-linear process. Like different quantum mechanics are involved in defining the quantum communication systems. More information can be found in this source uh, for understanding the quantum communication systems. So in this presentation, like I told you before, we are targeting the superposition-based quantum communication. So the quantum mechanics have been defined for qubits and quantum superposition. So more information again can be downloaded from this source. So qubits. So like in conventional system, we have two basic units, which is the qubits. In quantum, in classical bit representation, we have 0 and 1 to represent different states of the bits. And here qubit is like we denote as get 0, which is defined in 1 0. It's a single column metric. And qubit 1 represented as 0 1. So according to this quantum superposition theorem, the qubits can be 0 and 1 at the same time. So general state of the qubit superposition is given by get psi is equal to alpha times get 0 plus beta times get 1, where alpha and beta is a kind of random variable, and alpha squared plus beta squared mod of alpha squared plus mod of beta squared should be equal to 1. So the right hand side represents how that is possible in the quantum mechanics domain. So we can see that in the bit representation, we have 0 and 1. And in the qubit representation, where both 0 and 1 can happen at the same time in the quantum mechanics domain. So this is the proposed framework with a single qubit with classical channel coding. We have the information source and then source encoder. So in this source is an image that I told you before is coming from COCO dataset. In this simulation, we have used the images from the COCO dataset. And source encoder is we consider two encoders, JPEG and HEIF, with different quantization levels. We denoted as QP25, QP of 50, QP of 75, and QP of 100. So 100 defines the best quality of the image, and QP25 defines the least quality in this percentage. We have considered four levels of quantization. And then we have the classical channel code encoder. We use polar code here with half rate coding. Then we have the quantum encoder, like I explained before, the classical bits are mapped to quantum bits. And then we have the channel, quantum channel. And the receiver side, we have the inverse operation, the quantum decoder, classical channel decoder, source decoder, and the final information. Finally, we compare the received image against the original image using metrics like PSNR and SSIA, which are the common metrics used in image communication. So this is the proposed framework, quantum encoder. Quantum encoder, basically we use a Hadamard gate, which is a quite famous gate in quantum communication, quantum representation to convert the bits into superposition states. So Hadamard transform is given as 1 over square root 2 of 1, 1, 1, 1 minus 1. And we know the matrix representation of C get 0 and get 1. And we multiply them together to represent the qubit representation in the superposition state by multiplication of H and get 0. We get 1 over square root 2, 1, 1. If you do the same operation for the ket 1, so we get 1 over square root 2, 1 minus 1. So after the Q encoder, these are the two possible states for the ket 0 and ket 1. So now this information is transmitted across the quantum channel. So quantum channel, we considered, everybody considered 5 different levels of noise: bit flip noise, phase flip noise, depolarization noise, amplitude damping noise, and the phase damping noise. So all these 5 different types of noise are combined to generate the quantum channel. So I'm not going to discuss about the mathematics behind this channel representation, but basically we are using a kind of a quantum decoder based on the measurements. The probability of observed measurement outcome is defined like this equation, assuming the outcome M has been observed. The state of the system immediately following the measurement is given by this mathematical representation. And then for that, get 0 and get 1. So we are making two measurements, M0 and M1, which can be simplified like this. And then finally, we can do the measurement at the decoder and show that this can be simplified to uh, get 0 if you are transmitting get 0 if you don't have the noise. And if we have noise, we have to consider four different states. Get 0, we have to consider four different states, which gives like 1, 0, 1, 0, 0, 1, and 0, minus 1. Based on these measurements, we will decide which vector is close to the these possible four states, and then based on that, we do the decoding. So this is the proposed framework for the system with quantum channel coding. So in this part of the presentation, what we have done is we have removed the polar coding that I presented before with the quantum encoder and the quantum decoder. So there are few quantum channel coding is replaced with for the polar code that we considered before. So unlike in classical communication, the quantum channel coding happens after the quantum encoder. So information source encoder, JPEG or GIF, and then the quantum encoder, map them to the qubit representation, and after that we have the quantum channel encoder. In this case, we have used a stabilizer code as an example. And then the quantum channel and the receiver, we have the reverse operation. So these are the results of the qubit transmission with classical channel coding, polar code, and the quantum channel coding. And each row represents different quantization levels, QP25, QP25, different quality measurements, PSNR and SSIM, and QP50, QP50, SSIM, and PSNR, 75 and 100. In all four cases, you can see that the blue one represents the classical systems, JPEG and GIF, and the orange one represents the quantum with JPEG and quantum with the GIF. So you can see that there's a considerable gain in terms of the channel SNR compared to the equivalent classical systems. So this is the advantage of using quantum systems over the classical systems. So this is an example of how the image is decoded at SNR of 10, channel SNR of 10, and the quantization parameter we use is equal to 25 in JPEG image. For the left side, you can see that image has been completely deteriorated, while the right-hand side one is decoded using the quantum system, and there's no any errors happen in the image. So the next part is like we use the quantum channel coding instead of polar codes. So this graph represents how the two systems behave, polar codes versus stabilizer code, keeping the other system is unchanged. So you can see the quantum channel coding is much better than the classical polar codes. And similarly, this represents the similar performance like in the previous case with the quantum coding. And first row represents the PSNR of lossy and lossless. And first row of A, picture A represents PSNR of JPEG of lossy coding with polar and stabilizer codes. And B represents the same thing in the SSIM domain. So basically, these two represent the same information in a different quality metric, PSNR and SSIM. In both cases, you can see that quality observed using stabilizer code is much, much higher than the classical polar code system. And C and D represent the PSNR and SSIM with different codec GIF. So we can observe the same performance. And in the last row also represents the same thing for the GIF. You can observe the same information. So now we are moving into the multi-qubit encoding. So multi-qubit encoding is a quantum encoding technique that uses multi-qubits to represent the information, enabling higher throughput. So this is quite analogous to the uh, higher order classical modulation systems where we have BPSK, QPSK, and 256 QAM and so on. When you increase the order of the modulation, the throughput goes up. A similar concept has been used in quantum systems as well. In this case, multi-qubit encoding has been used to combine different qubits in a high dimensional space so that we can increase the throughput of the system. Why multi-qubit encoding for image transmission enhances the system robustness by distributing information across the quantum states in a high-dimensional Hilbert space using the superposition, improve error resilience and noise mitigation, reducing the impact of localized disturbances, and support advanced encoding systems and better scalability in enabling reliable transmission over long distance and in noisy environments. So the methodology is same, other than the quantum encoder has been replaced with the multi-qubit encoder. So we have the original image source encoder, JPEG or GIF in this case as well, and channel encoder. And then we have the multi-qubit encoder, which combines several bits into multi-qubit representation. We have the quantum channel. At the receiver side, we have the reverse operation, multi-qubit decoder, channel decoder, source decoder, and reconstructed image. So I just use one example here to show how it works for two qubit representation. So in single qubit representation, 0 and 1 is represented by 1, 0 and 0, 1. And 2-bit qubit representation, we take the tensor product between 0 and 0. There are four possibilities like in classical system, 0, 0, 0, 1, 1, 0, and 1, 1. So these four states are defined on the right-hand side by taking the corresponding tensor product. So for example, if you have 0, 0, 0, 1, 0, tensor product 1, 0, we get 1, triple 0. For example, 1, 0 means we have get 1, tensor product with get 0, giving the vector, single vector column is 0, 0, 1, 0, and so on. There are four possible scenarios here. So once you get that, also now we have to consider the 2 by 2 Hadamard transform, which can be calculated using the tensor product between H and H, and that's how we get the 2 by 2 Hadamard transform for multiplication. Once you calculate that, so you can get 2 qubit encoding by considering the Hadamard transform 2 by 2 Hadamard 4 by 4 Hadamard transform by 4 by 1 vector to generate 4 different states for 0, 0, 1, 0, 0, 1, and 1, 1. So finally, the information is transmitted using the Q channel, quantum channel, like I explained before. So in the decoding process, we do the same thing. The corresponding Hadamard gate again it can be used to extract the quantum states from the qubit representation motion states, because the inverse of the Hadamard gate is the Hadamard gate itself. So therefore, by multiplication of these two gives you the received output, in this case 1, 1. So in a noisy situation, similarly, we can apply the Hadamard gate to the noisy superposition state, allowing the corresponding state to be mapped into the nearest preferred quantum state, like in the Euclidean distance calculation in the classical domain. So afterward, the recovered quantum states can be correctly mapped to the corresponding qubits using Euclidean space, as these states lie in the computational basis and are directly related to the classical data, from which the classical bits can be extracted without any problem. So these are the results for the PSNR and SSIM and channel SNR for different multi-qubit representation from 1, 2, 3 up to 8. So you can see that uh, when you increase the SNR, multi-qubit representation is quite efficient in transmitting the information. But if you keep on reducing the SNR, so they completely failed after a certain threshold of SNR, which is the same behavior like in higher order modulation schemes in classical systems. So if you want, you can combine the impact of all these multi-qubit representation based on the SNR. For example, at low SNR, you can select the lower qubit representation, and high SNR, you can switch it to the high multi-qubit representation to improve the throughput and the efficiency. And this is with the channel coding. So you can see the SNR axis, channel SNR, everything can be shifted to the left side to give better performance against the SNR. So this one represents the PSNR and SSIM of the uncoded information. You can see that this is without the compression. We can get up to minus 6 dB without any problem in transmitting the images. And this one is with the coding. So you can see that the improvement can be happened by further reducing the SNR. So what is the conclusion? So increasing the number of qubits used in encoding results in significant improvement in both error resilience and image quality when compared to the single qubit encoding. The system supports an arbitrary number of qubits. This study utilizes the qubit encoding sizes from 1 to 8, ensuring constant bandwidth uses across all situations to have a fair comparison. The system achieves its best performance with 8 qubit encoding at high SNR for high noise resilience environments. However, this improvement increases the complexity and the resource usage, as you can imagine. The channel coding, this setup delivers up to 15 to 17 dB gain for JPEG and GIF images respectively compared to the single bit encoding. These improvements results from the combined benefit of multi-qubit encoding, error correction, and the compression efficiency. So what is the future work related to this domain? We haven't investigated the quantum channel coding with multi-qubit representation, because in one way this is going to be heavily complicated. But nevertheless, that will give you further improvements compared to what I have presented today, aiming to enhance the performance without introducing unnecessary complexity. Explore next generation quantum compression techniques and immersive media formats to evaluate the methods adaptability across diverse applications, including video transmission. Video transmission is the next immediate target for us, how the video will behave in quantum multi-qubit communication systems. So that concludes the presentation. Thank you very much for listening to this presentation. If you have any question, you can email me, or if you are open for any collaboration, please also email me. I'm very much open for international and national collaboration in this domain or any other domain that I have explained at the beginning of the presentation. Thank you very much. So I'm signing off from University of Strathclyde in Glasgow, and have a nice day. Thank you.